Hi everyone, my name is Meng from UCLA. Today I'd like to share our work, an integer linear programming framework for mining constraints from data. This is a joint work with Professor Kai-Wei Chang. In many machine learning tasks, the output labels follow certain constraints. These constraints define the output structure or encode the domain knowledge. For example, in dependency parsing, the output labels form a tree structure. In part-of-speech tagging, the constraints can be used to specify that each sentence must contain a verb. In multi-label classification, constraints can be used to describe the hierarchy between the labels, such as an image labeled flower must be labeled as a plant. In most prior studies, constraints are given by domain experts. In this paper, we study how to automatically mine these constraints from input label pairs. To solve this problem, we propose an integer linear programming framework for mining constraints. ILP is general and can be used to describe inference in mining structured output prediction tasks. The formulation of ILP is that we want to optimize the inner product of W and Y with a set of linear constraints, where W is the weight of the objective function and Y is the structure output labels. The weights are usually scored from local predictors. The matrix A and B describes the constraints that Y need to follow. In this paper, given WY from training dataset, our goal is to identify underlying A and B that describing the problem structure. For example, given a JSON matrix of a graph and its corresponding minimal spanning tree, we pose a question that whether we can learn that this is an MST task and identify A and B representing a tree structure. Instead of estimating A and B directly, we estimate the feasible set defined by the constraints. Basically, we find an outer and an inner polytope and squeeze them towards the feasible set. Here, the red polytope stands for the feasible set. A data point WY is given here. W is the direction and Y is the optimal solution in the feasible set. Given three WY pairs, we can find an outer polytope and an inner polytope of the feasible set, and both of them are triangles. Each pair gives us a half space for the outer polytope and one feasible point in the inner polytope. With more data, we can cut the outer polytope and enlarge the inner polytope. In the test time, we will make prediction based on the estimated polytopes. We also propose two complementary methods. One is for mining equality constraints by linear algebra methods. Another is to introduce latent variable to simplify ILP formulation. Please come to our poster or refer to our paper for more details. We first test our framework on two synthetic problems, MST and Sudoku. In both cases, WY pairs are directly generated, and our goal is to learn the underlying constraints from the examples. For MST, we found that our approach can successfully identify the tree structure of MST solutions and achieve 90% exact match accuracy with 20,000 examples, while neural network counterparts has the trouble to solve the problem. Similarly, given Sudoku puzzle without giving the rules, our approach is able to identify the underlying rules with 9,000 examples. Please see our paper for more details. We then test our framework on a multi-class classification task, where the labels follow certain hierarchy. In the inference time, the local classifier provides a local score W for each label. The selecting of the final output labels is based on the local scores as well as some hierarchical constraints. Our goal is to identify these constraints and improve the model prediction accuracy. The baseline model conducts inference only using local classifier, while our method learns the constraints and captures the pairwise label correlation using the training data. Results show that although the learned objective weights can be noisy, Our framework is able to identify constraints, and the performance improved from 74% in baseline to 81% with mined constraints. If you are interested in our work, please check out our paper and code here. Thanks for your attention.